The claim. When a researcher conducts a study, he or she is generally looking at evidence to support a claim. I'm going to make a claim that my installation is going to lower your bill. Therefore, the claim should be stated as the alternative hypothesis or the research hypothesis. A claim, though, can be stated as either the null hypothesis, like I said with the the self-esteem. I may want them to be closer to the normal mean. So it may be the null hypothesis that I'm making the claim. So it could be either the null hypothesis or the alternative hypothesis. However, the statistical evidence can only support the claim if it is in the alternative hypothesis. So I can only support things that are significantly different. So I can actually claim in my self-esteem study that, yes, the groups were significantly different in the beginning. Now they're not. So I would still have that claim as an alternative hypothesis. Statistical evidence can be used to reject the claim if the claim is the null hypothesis. So the correct terminology here, and this can be a little confusing, is if I have statistically significant results, I'm going to reject the null hypothesis. So I no longer can say that the null hypothesis is true, my alternative hypothesis is true, so I'm going to reject the null hypothesis. However, if I have to accept that there is no difference in the means after my research is conducted, I have to fail to reject the null hypothesis. And that's the jargon that we have to use. So it can be a little confusing. So if I fail to reject the null hypothesis, basically I'm accepting that there is no difference. But if I can go ahead and reject the null hypothesis, I can say that yes, my findings are statistically significant and there are statistically significant differences in the means that I'm studying. These facts are important when you are stating the conclusion of your statistical study or when you send in your results or you write up your results. Hypothesis testing. After stating the hypotheses, the researcher's next step is to design the study. What statistical test are you going to use? So the correct statistical test. And this depends on many, many factors. Like I said, if you have a small sample and you're testing two means, you're not going to use a z-test because it doesn't represent a normal population. You would have to use what's called a student's t-test. Now, if you're testing more than two means, so if you're testing three means or more, then you need to use something else like an ANOVA, an analysis of variance. And if you're testing qualitative data, categorical data, then more than likely then you're going to be using what's called a chi-square. So depending on what you're actually testing is going to determine what your statistical test is. And then you would choose an appropriate level of significance. And what that means is the significance level is your alpha level. So do you want to be 95% accurate when you report your findings, or do you want to be 99% accurate when you report your findings? And basically, what are you willing to accept as error? So like I say, in the social sciences, we accept about 5% error. It's okay if I'm dealing with variables, and I could be wrong 5% of the time, which is okay for me in the research that I do because I'm not dealing with life and death. I'm working with behavioral problems. However, a medical researcher, they may not accept 5% error because they may be dealing with life and death. They may want their alpha level to be much smaller, like 1/10 of 1% or something like that. So as the alpha level gets smaller, or that level of significance gets smaller, there's less likely a chance for reporting findings that are not true. A statistical test uses the data obtained from a sample to make a decision about whether the null hypothesis should be rejected. And so once we get our data, we analyze it, we know that, okay, I can clearly state that these means are different. So if the means are different, then I'm going to go ahead and say I'm going to reject the null hypothesis, and report that I have statistically significant results. The numerical value obtained from a statistical test is called the test value. Whatever, it could be a z value, a t value, an f value for the ANOVA, or a chi-square value. Or we could be looking at regression analysis using a y variable and an x variable, and we can be looking at relationships between variables. And then we can make some predictions in the future about those. In reality, the null hypothesis may or may not be true. A decision is made to reject or not to reject the null hypothesis based on the data obtained from a sample. A type 1 error occurs if one rejects the null hypothesis when it's true. And like I say, we're not going to know that. The only person who's going to know that is a great statistician in the sky. We don't know. So if I made a type 1 error, I don't know. So that's called an alpha error. A type 2 error occurs if I do not reject the null hypothesis. Let's say I accept the null hypothesis, but really my findings were that the means were significant. That's called a beta error or a type 2 error. This is like a Johari's window. We've got, if the HO is true, I made a type 1 error if I reject the null hypothesis. So my null hypothesis is false, I reject it, I made the right decision. So, and like I say, we're not going to know that. This is all hypothetical, and we just don't know. But we want to do our best not to make a type 1 or type 2 error. So with a type 2 error, I make the correct decision if I fail to reject the null hypothesis when the null hypothesis was true. I did not accept it. It is true. I made the correct decision. However, if I do not reject the null hypothesis, or I fail to reject the null hypothesis and it was false, I made a type 2 error. Again, the only one that's going to know that is a great statistician in the sky. A level of significance is the maximum probability of committing a type 1 error. And like I say, p-value is going to determine, what's the chance or what's the probability of making a type 1 error. So the probability is symbolized by alpha. That is a probability of making a type 1 error is alpha. So if I set alpha at 0.05, there's a 5% chance that I could, or there's a probability of 5% that I could make an error. So when we're looking at probabilities or p-values, anytime you see the p-value, and if it's less than 0.05, it will say p is less than 0.05, then I know that my means are significantly different. Likewise, p type 2 error is a beta error. So, and when we're looking at power, that's when we're going to be looking at beta. So if I set my alpha level at 0.05, just the opposite of 0.05, is like 95. So type 2 error, beta error, usually associated with level of power. Statistical significance levels are 0.1, which I've never seen a research study with like 0.1. 0.05 is usually found in social sciences, and then 0.01, that's when you want to tighten up your level of error and you want a stronger study. Medical researchers, people dealing with more sensitive material may want to use a alpha level of 0.01, where there's only a 1% chance that they'll make a type 1 error, but there's a 99% chance that they're reporting the true results. For example, when alpha is set at 0.1, there is a 10% chance of rejecting a true null hypothesis. Not good. 10% is not really not something that you really want. So 5% would be much better. That means that 95% of the time that you're going to be producing the right true results. The critical or rejection region, this is the range of values of the test value that indicates that there is a significant difference and the null hypothesis should be rejected. So we're going to move into means, and I'll talk about means in just a minute. So if we have a non-critical or non-rejection range, that is the range where there's no significant differences between means. So the range of values of the test value that indicates that the difference was probably due to chance. It wasn't due to my research or my independent variable. It was due to some other variable that I didn't control for, or some nuisance variable or something like that. And then we have what's called the critical value. The critical value separates the critical region from the non-critical region. That means if my mean falls into the critical value or the critical region, then I have significance. I know those two means are different. And here we go. We're looking at a curve, and once I find my appropriate test parameters, then I will know based on what I set my alpha level at, and this person set their alpha level at 0.01, 1%. So that's going to push this region of rejection way out to the positive tail here. So basically, if I test my hypothesis and I get a new distribution of scores from a sample, and I test the mean, and I find the mean falls within this critical region, then I know that there's significant differences. If the mean falls in this non-critical region, I can say that there's no significant differences, or the differences, if they're over here somewhere, are due to chance and not my research. And now we can look at, this is like the closest value to 99, so that's what we're looking for is 99%. We can find that we're looking for a z-value of 2.33. So 2.33 would be the correct z-value for an alpha level of 0.01, and that just means that 2.33 standard deviations to the right of the mean would be my critical value, or my critical value, and it would set my critical region for anything beyond 2.33 standard deviations from the mean on a z distribution.